Today, we are continuing our journey into electromagnetism, and we will derive the wave equation and hopefully also solve them. And the wave equation that we will derive is the wave equation for electromagnetic waves. And I can easily refer back to previous lecture before the second exam, where we said, well, if we have a time varying magnetic flux, that will induce an EMF/electric field. And if we have a time varying electric flux, that will induce a magnetic field. And those two things together, they can talk to one another. So just taking those two things together, we'll be able to come up with a wave equation for either the electrical part or for the magnetic part. And it cannot be overstated, even though I'm going to try really hard. It cannot be overstated that the wave equations that we will find will be one for the E field and the other for the B field. And even though we might be tempted to think that they're two separate equations with their own solutions, that's of course not really true, because as soon as you lock in what the E field looks like, that immediately means that you know what the B field looks like. So you can solve either one of them, but don't solve them independently. So electromagnetic waves, obviously that's the that last part that we needed in order to get to the wave equation was the fact that these time varying electric flux goes through Amperian surfaces can induce a magnetic field through that addition of the displacement current to Maxwell 4, which now is known as Ampere-Maxwell's law. That was the missing component, right? Because if we need to get this circular thing going where we have time varying magnetic field causes time varying electric field, then we also need to go from time varying electric field back to magnetic field. Otherwise, we cannot get them to talk to one another. So that was the beauty of Maxwell's addition to that to that fourth Maxwell equation, and that's the thing that will get you to electromagnetic waves. Now, electromagnetic waves, the fact that those came out are really something special, and I hope you realize that. So this is also one of the reasons why electromagnetism is one of my favorite subjects, because it's one of those subjects that very clearly takes these very distinct things, so how charges interact, how magnets interact, how charges interact with magnets, and vice versa. And then somehow at some point when you've made that into a coherent framework, pop, out come electromagnetic waves and all of the optics that comes with it. And if you didn't know that, you didn't see that coming, so where did that come from? So just by putting them together in a coherent framework, oftentimes will allow you to all of a sudden discover that there was all this other stuff that you might not have considered as being part of electricity and magnetism, that all of a sudden also is described by electromagnetism. And that's one of the reasons why I like it, because it's so all-encompassing. And it's also for physicists, it's always still probably their first encounter with unifying theories, right? Where you can take where you can try to come up with the most general description of the way nature works, that can the most compact formulation that can describe the most wide range of phenomena around you. And it's this is one of the big searches in theoretical physics, is to try to figure out a single equation that can describe all of the forces. So we're not there yet. I lost track of how many forces we've unified, but one of the biggest problems is that we still cannot get gravity to behave in a quantum realm. And that's a completely different graduate course in field theory. But back to electromagnetism, the wave equation that we'll get to today, we will use a couple of simplifications, and those are needed because most of you will not have seen the del operator yet. If you have, you can actually work in the differential form of Maxwell's equation. So I mentioned this before, where you can take Gauss's law, Ampere-Maxwell's law, Faraday's law / the circuital law, and you can reformulate them using Stokes and Green's theorems into differential form, also known as local form. So no more integrals. And if you use that, you can actually do what we're going to do today. You can do that in a much more compact manner. But because sometimes this course is a little bit out of sync with what you are learning in Calc 3, if you learn it at all, it's a good idea to also have seen this in the form where we don't use the del operator or the nabla operator. You know, it's the upside down delta. And do this in integral form. So that's what we will do. And then when we do our, when we do solve the wave equation, I want you to realize that the technique that we will use is called separation of variables. And hopefully this is not a brand new thing for you, but I'll go slow. Separation of variables is really nice for differential equations where you have derivatives with respect to different coordinates. So we will have a differential with respect to z, so position, and we'll have one with respect to t. And we'll use separation of variables to literally separate those, and then such that you get two differential equations, one for t and one for z, and then you can put the whole thing together, stitch it together. So separation of variables, it's a really, really good technique, and it works really, really well, except the one thing that you need to remember is that separation of variables, if it gives you a solution, is not guaranteed to give you the only possible solution. So just be mindful of that. So the wave equation, let's see if this works better. I don't think that's actually better. No. The wave equation. When we last left Maxwell's equations, we had two formulations. We had the ones with sources, and then we had the ones without sources. And then there was Maxwell 2 and Maxwell 4, which had that time derivative in them that I told you to pay attention to. So Maxwell 2, sourceless, says that if you have this time-varying magnetic flux, then that will give you an EMF, which is an electric field, right? So that is ddt of BDA is going to give you an electric field. Now I'm putting the minus over here because I like writing it like this for this particular exercise. Okay, so remember that this was over some kind of a surface, an Amperian surface. So this was over some surface S, and this was over the edge of S, and this is Amperian surface. Okay. And this describes that what I was saying before, that if you have some time-varying flux, that's going to give you a time-varying electric field. And now Maxwell 4, sourceless, says the reverse, that if you have a ddt of EDA, which is ddt of phi e, but for a Amperian surface, that is generating a magnetic field. But I'm moving the U naught over epsilon naught over to this side, and I'm going to put a ddt here, and that's going to give you a BDL, obviously, BDL. Okay, and again, this now is a surface, so that's over a surface, and this is over the edge of a surface. So that's how they're related. And both of these are for Amperian surfaces. So we've had this flux E. We haven't really talked about this electric flux too much in the context of Amperian surfaces, but it should be clear that it's just flux is always the field integrated over surface area, and then what the geometry of that surface is going to determine whether that's if this is a Gaussian surface or an Amperian surface. It's going to look different. And if it's an Amperian surface, you're talking about, in this case, Maxwell 4. If it's a Gaussian surface, you're actually talking about Gauss's law, aka Maxwell 1. All right. So that's the that's the most general setup. So in general, we would like to have some kind of an electric field. So let's see if we can draw that like this. So we'll have some electric field, which is a function of position and time. And then simultaneously, we have a magnetic field. Let me use this one. Magnetic field. So that's this one, which is a function of position and time. So that's the most general form. So we have a B here, and a B here, and an E here, and an E here. Okay, so causally, it's going to go from E to B, B to E, E to B, B to E. Okay. Now, in order to get the wave equation, we're going to make a couple of simplifications. We're going to make it a little bit easier. So for the electric field, we're going to limit ourselves. So we're going to say limit to. We're going to say that the electric field is pointing in the x direction. So that's the E field, and it's only a function of the z coordinate and the t. You can call it the coordinate. And we're going to also limit the B field, and we're going to limit that to a field that points in the y direction, and then is also only a function of the z and the t coordinates. So we're using the most general description of those fields, and now we'll limit it to this. Okay. Now, in order to connect these, we need to look very carefully at what this looks like in a coordinate system. So we're gonna draw this. This is the x-axis. This is the y-axis, and this is the z-axis. So you notice that I've drawn them in different direction. Now, if the E field's pointing in the x direction, that means that the E field is pointing like this. And if the B field's pointing in the y direction, that means the B field's pointing in this direction. All right, so they're perpendicular to each other, but it should be obvious that B pointing in the y direction is because of this simplification. Okay. Now, let's look at what that means for a surface. So, for instance, we can choose a surface, an Amperian surface. We can choose it in any one of these planes, right? So we can choose the xz plane, the zy plane, and the xy plane. We can also pick something completely different, but let's try to be intelligent about it. So, for instance, in this case, the normal here, BDA, the normal here is pointing perpendicular to that surface. Sorry, it's pointing in the same direction as B, that you'll get the biggest flux. So if we use as this first surface a surface that is set up in this direction, so do this like this. And these are all right angles. And then we're going to call this surface 1. Surface 1. So that means this is surface 1. This is surface 1. And this has a surface area, obviously. And now we're going to see what it looks like if we go from we do the contour integral and if we do the surface integral. So the let's look at the contour integral first. So the if we're starting in this point and we're going up, out, down, and back again, that means that if you use your right-hand rule, that means that you're describing a surface where the normal is pointing according to the right-hand rule in the direction of B. So let's do that. So we're going to go perform that integral in this direction. So the so that normal is pointing in that B field. Okay. So we start here. We let's repeat the DDT, DDA. Actually, let me start color coding it because it's going to get confusing. DDA causes a minus contour integral EDL. All right. So we're going to do this first part first. So this EDL is integrated over here. That first part, the path is perpendicular to E, so that doesn't do anything. The integral in this direction is exactly in the direction of E. So that is whatever the E field is at this location. So we're going to call this here, we're going to call it E Z plus delta Z. Actually, let me do it at 0. T E Z of T. So when we start in the origin, we go up. There's nothing added to the line integral, but then we go in this direction. We add whatever that E field is times the length of that path. So let's call the length of that path dx, delta x. So that means we'll get minus. All right, there we go. It's E at delta z t times this length, delta x. All right. And then again, for this part, we're not getting any contributions to the line integral because this path, the dl here, is perpendicular to E, so it doesn't do anything. Same thing here, dl perpendicular to E. All right. So then the last part is this fourth section. We're going in the direction opposite to the electric field over the same dx. So we're doing minus delta x, and this is the E field, but now this is the E field at 0. Okay, for simplicity's sake, we'll keep this we'll keep this centered at the origin, and then we will generalize this later. Okay, now that's the right hand side. So that's the E field that this B field is going to generate. So what about that B field? Well, that B field is going to be the B field integrated over this surface area. So that is going to be ddt, and then the B field. Now this becomes a little tricky. In the end, what we will do is we will take the limit of this delta x and this delta z going to 0. So we'll end up with whatever the average field is as that surface area tends to 0. So I'm going to use the field integrated over this area as the average field. Okay, so that is B. And integrated over the surface area, so that is times delta x, and then delta z, which is the this path, delta z. Okay, so this delta z, delta dx. Okay, now this doesn't look like much yet, and that's because of this difference here. So we can't really do much with this difference because we can't really subtract these two terms yet. But what I was saying earlier is that in the end, we'll take the limit where delta z goes to 0. So let's write E as a Taylor expansion. So we'll do a Taylor expansion. For E. So we'll get E delta z t is E at 0 plus delta z times d dz E evaluated at 0. This becomes very tiny. So that's Taylor expansion always, right? So you have a Taylor expansion at some distance from your reference point, and in this case, the reference point is the origin. So you start at whatever the value is, and then you take the first derivative evaluated at that point, so that's 0, and then you multiply that by delta z, so you're basically making a straight line expansion. So if we put that in there, so that's the Taylor expansion, if we plug this in here, you'll see that we get the difference of this minus this. So in other words, this minus that. In other words, this. So we will get, on the right-hand side, we'll get minus delta x. And now, so I factored out the delta x. It's this minus this. So this minus that is this. So we'll have delta z. And now we'll have the ddz of E at 0. Okay. Now, you see that we have a delta z and a delta x here, and a delta z and a delta x here. So that means that we can drop those two terms. So we can, let's see, drop these and drop this. And now we have time derivative of b gives you a spatial derivative of z. So turns out it's not too bad. It's not too messy. It's it looks like it's going to get more complicated when we throw in the Taylor expansion, but actually turns out to actually clean it up a lot. So that's the first part. Now the second part is the thing where we'll take a Amperian surface that's going to be perpendicular to E. So let's do that. So this is surface 1. Okay, let's do surface 2. So we'll do the ddt of E. Right, that's an EDA. Is 1 over mu naught epsilon naught, and then the integral, and that is the oops, I forgot a contour of B dl. So has the same basic form, except this one has the extra mu naught and epsilon naught, and that's going to turn out to be important. Okay, so we got this causes that. So let's do the same thing that we were doing before. So this first part will take over this surface. So let me draw that as a blue surface, because, you know, what is a Postma lecture if I haven't used all of my colors? All right. So this is surface S2, and it's blue. So this is S2, so that's this one, S2. And this is the S2 edge. All right. So we'll do the same thing here, and we'll get for a delta y in this direction and the same delta z in that direction, we'll get a ddt of E. Now I'm doing the same thing. I'm going to take it at 0, and we'll multiply that by delta y and delta z is going to cause, now we'll do the right side, so there's a 1 over mu naught epsilon naught, and here we go. We'll have, again, this contour, and that's a contour integral, right? That's the edge of this surface. And using, again, our right-hand rule, E is pointing right at you, or rather, sort of at you, which means that according to the right-hand rule, we'll have the right sign if we go in this direction. So do that in this direction, and then here we'll go down. Okay. Now, this first part, it will be in the direction of the B field. So it's going to be delta y times B. So times B. Now that's B, but that's at 0. Oops. Sorry. And then we go up here, but here B is perpendicular to DL. So that gives you 0. So this part gives you 0. Here we're going in the direction opposite. So we'll do a minus delta y. And now this is B, but it's not at 0 anymore. It's at delta z t. And now we can do the same thing. We can make a Taylor expansion. And that means we can write B at delta z t is B at 0t plus delta z times the derivative with respect to z of B evaluated at 0. Okay, so that's this one. Now, here we have the reverse of what we had here. So we have B0 minus B delta Z. So it's this minus this. So that's minus this. So we'll pick up a minus, and we'll get, finally, minus 1 over mu naught epsilon naught delta y delta Z ddz at B at B of t. Okay, so we have now two equations. We have reduced, for this very specific case, we have reduced our causal relation that was initially set up by Maxwell 2 and Maxwell 4. We've reduced them to something in, where did we go? This form or this form. Okay, so these are the ones that we will put together. So let me copy those over, and then we can start putting them together. So our first one, which was Maxwell 2, but then in heavily reduced form, says that ddt of B at 0t, this is not supposed to be there. We dropped the delta x and the delta z is equal to, now we have left here this thing on the right, so that is minus ddz of E, use that in green, 0T. All right, so that's what was left of Maxwell 2. Now, what is left of Maxwell 4? That's the last one we did. Well, let's see. We have the delta Y and the delta Z. Again, we can drop those because they show up in both of these. So we have a ddt of E. And that's a minus 1 over mu naught, epsilon naught, ddz of B. Zero T. Okay, so that's what was left of these of the two Maxwell's equations for this highly idealized equation. So ddt of B going to give you this, ddz of that is going to give you that, and then oops, sorry, this is a T, not a Z, and it's important. Okay, so now we're going to it's time to put these together. Hey, dropped my color convention. I do apologize. That's green. Now we can either try to eliminate B or we can try to eliminate E. I have a personal preference for E, so we're going to try to figure out a way to get rid of the B field. How do we do that? Well, you see, if we take the spatial derivative of this equation, we'll get a ddt ddz of B. And if we take the time derivative of this equation, we'll get a ddz ddt of B. So in other words, we'll get the exact same equation. So we'll do this, and we'll take the ddt of this. So I'm out of space. I should have put it here. Ddt. Let me put that here. Ddt. And now we'll do ddz of this one. So we'll get ddz ddt of B equals minus ddz squared, right? Because we do 2 times derivative now of E, so that's E. And this is B. Okay, and if we do that here, we'll get a ddt squared of the E field is minus 1 over mu naught epsilon naught d t d z of B 0T. And this is also 0T. So now I hope you see that we have the same thing here, except for the mu naught and epsilon naught, as we have here. So we can eliminate the B field by equating these ones. So this one, we just need to multiply it by times mu naught epsilon naught with a minus times minus 1. So then this term is identical to this term. And then this will be equal to that. All right, so let's do that. So we'll have on the left-hand side minus ddz squared of E. Now on the right-hand side, we'll have, we're eliminating this one. So that means we'll pick up a minus here as well, minus mu naught, epsilon naught. And now we'll have a dt squared, oops, drop the square, ddt squared of E. Now we're almost done. Now, remember what I said is that we were doing this at the origin, and there's not really a reason to do that there. We could move it at any point because the origin in this case is not really that different from others. So we can actually just say this also holds at Z. And now we have the wave equation for E. That's the wave equation for E. So while we're at it, let's try to figure out if we can get the wave equation for B. So in that case, what we want to do is we want to start with this one, and if we want to eliminate the E field, then we need to make the this equation and this equation, that derivative of the E, look the same. So let me repeat what I had here. So I had a ddt equals minus ddz, and then I have a ddt equals minus 1 over mu naught epsilon naught ddz. All right, so this is our B. This is our B. This is E. And this is E. All right. Now, if we want to eliminate, E in favor of B, that means we need to make this derivative look like this derivative. So we take the temporal derivative of this one, and we take the spatial derivative of this one, ddz, and now these two look the same except for a minus, so times -1, and then we can equate them, and we'll get a where'd my minus go? Ah, yes. Okay, so we'll get a ddt squared of B equals 1 over mu naught epsilon naught ddz squared of B. And that's B. And that is the wave equation for B. All right, let me make sure I didn't sweep anything under the rug here. Yeah, that's correct, because we have a minus here and we have a minus here. So we're gonna make this negative. That means this one becomes positive. So that's positive, positive, positive. Okay, good. And then we do the same thing here. We'll say, you know what, this also holds for this one. Okay, so these are the wave equations for E and B. Now we have the wave equation for the electric field, and we have the wave equation for the magnetic field. I did write it a little bit funny, but don't worry about that for now. So let's look at the wave equation for E first. Like I said, I'm partial to the wave equation for E. I'm going to make a change here, and I'm going to say that 1 over mu naught epsilon naught, I'm going to call that, by definition, C squared. It's going to make life a lot easier, because then I have to, I'll keep writing that. And it also has physical meaning, but we'll get to that in a little bit. So you see that in this case, I had the ddz squared on the right-hand side and a 1 over mu naught epsilon naught. And here I have the ddz squared on the left side and I have a mu naught epsilon naught. So these are actually identical. It's just that mu naught and epsilon naught show up on the opposite side of the equal sign. So these two are the same. Okay, now we are going to solve this monster. And I prepared you already. I said that I was going to use a technique known as separation of variables. And what is separation of variables? Well, I'm going to tell you. So we have the equation for E. I'm going to stop using green because now we have E only and should be easy to figure it out. So I'm going to bring the C over to the other side, and I'll have C squared, and then I'll have a ddz squared of E. And I'm going to stop writing the coordinates because, well, actually, might as well first do it. It's proper. So I brought it over to the other side, the C squared. And then, yes, I did that right. That's a ddt squared of E, also of Z T. So the separation of variables is, we're going to assume that we can say that E, which is a function of both these coordinates, is actually the product of two functions, one exclusively dependent on the Z, and the other exclusively depending on time. And you'll see in a little bit why that is useful. So if we assume this, then if we put that in here, we get a C squared ddz squared of Z T G, all right, is equal to, oops, that's a squared, ddt squared of, again, G T. Now, if I take the derivative of this with respect to Z, then this thing is not going to do anything. So I'll end up with a C squared T of T. And now the second derivative of that big Z equals, same thing here, except now we have the ddt only acting on this one. Z. Now we have the d squared T dt squared. And now there's something special that has happened, and I don't know if you can see it yet. On the left-hand side, we have a derivative of Z and the original function T. On the right-hand side, we have a derivative of T and the original function Z. If we now divide both by the product of T, then what that means is for the left-hand side here, we'll divide out the T and we'll end up with the Z in the denominator. So we'll end up here with a C squared, 1 over Z D squared Z squared. And now on the right-hand side, we'll have gotten rid of this one, but we'll have a 1 over T. And then this is dt squared. And now this is why they call it separation of variables, because this only depends on Z, and this one only depends on T. If this side only depends on T and this side only depends on Z, that means that if this one depends on Z and the right-hand side only depends on T, then what is on the right-hand side, because it doesn't depend on Z, should be some kind of a constant. And the same thing here. This should be some kind of a constant. And now the next question that we usually say, okay, what are we going to call this constant? Let me rewrite it a little bit. I'm going to put the c over on the other side, and I'm going to use shorthand notation for the derivatives. So I'm going to say z double prime, because it's the second derivative of z, and the z has only one argument because it's only z. So double prime should be unambiguous. Before, you didn't know which derivative we might use. Is 1 over c squared. And now we'll call this t, and this is again the second derivative of t and t. Okay, so since this does not depend on z or t, we can now solve these differential equations separately. So we'll have z double prime minus lambda z is 0. And that is a very straightforward differential equation. And a second. We also have a t minus lambda c squared t is equal to 0. These are our two differential equations. Now we have to be very, very careful. There are usually two ways to do this. There's a z of z equals, so I'm going to say this is lambda z. But we have not actually decided what the sign of lambda is. So if lambda is positive, then there's really only one type of function that if you take the derivative, you get the original function. If you take it twice, you get the original function twice, and there's no minus sign. Then z is some kind of an exponential, some e to the power z with something. And if we use this one, smaller, there's only one type of function, or if you want to call it two, and that is the cosines and the sines. So it's z is going to be some kind of a cosine of z plus b sine of z. Now, this might look like, why are we even doing this? Why are we even considering the sign? Well, because it's important, because one, you get an exponentially varying function, and then this, you get something that is cosinusoidal, sinusoidal, depending on what the boundary conditions are. Now, the cool thing is that because you now know the power of complex numbers, we can actually take this one and write this as an exponential, and then assume that if we take the square root, because we have to take the square root of whatever came forward once, and if that number is negative, that means that we'll get a complex number. And if you have a sum of complex functions like that, you'll find cosines and sines. So if you're super consistent, and I'm not actually going to walk you through that line of argument, because it gets a little messy and a little tedious. If you're super consistent, it doesn't really matter if you use this one, and you'll end up with that one anyway. So I'm going to use this assumption because I'm looking for waves, but it's not the only way to do it, and it's also not the only type of solution that we will get. Okay, so we'll use this one. In that case, we'll get z double prime equals to lambda. So let me call lambda minus kappa squared. So it's clear that it's a negative number, and we'll need the k twice because we'll have the second derivative, z of z. then the most general solution to this is some A cosine kz plus a B sine of kz. All right. Now, at the same time, do the same thing for t. Now we have t here, except for t, we have an extra c squared. So we'll have t, is equal to minus c squared kappa squared t of t. All right. And that means that the most general form of this looks again like some kind of a cosine. So let's call it big C cosine kct plus d sine kct. Now our most general solution to this is the product of these two. So therefore, E, which we were solving for in the first place, is the product of that Z and the product of that T is going to be, hold on to your hats, A cosine kz plus B sine kz C cosine kct plus D sine kct. So that's the most general solution. Except if you look at this, this does not look like it's a wave equation, or it doesn't look like a traveling wave yet, because we've got products of cosines and sines all over the place. So a way to solve that is to actually use the complex notation. So then we can kind of pull things together. So let's do that. So we'll say the cosine kz times A is, we're going to call that e to the power I kz plus e to the power minus I kz. And now, strict't speaking, what I should do is carry this A forward to the other side, except then we're going to have to carry T's everywhere. So I'm going to call this thing differently. I'm going to call this thing A, C, CZ, and we're going to call this B, CZ. And now we'll do the same thing for the sine. So we'll do B sine kz equals, well, this one is a little different. It's e to the power I z minus e to the power minus I, kz, minus I kz. And we're going to do the same thing here. We'll call this B sz, and we'll call this A sz. All right. And then we have the same thing here. We're going to call C cosine kct. We're going to call that C ct e to the power I kct plus e to the power minus I kct. And we're going to call this d ct, and we'll do the same thing for the sine. Sine, that's not a C, that's a D, kct. is equal to C. Oh, I did. Yeah, I used a different one. C T e to the power I k c t minus e to the power minus I k c t C. Nope, D. Do apologize. It gets really messy with all the subscripts. D S T. Okay. Now we need to multiply this thing out to get this thing. All right. Now this is going to get really even more messy. So let's try to see if we can see what's going to happen. So we'll do this term plus this term. So this plus that times this plus that. So we're going to get cross terms all over the place. So we'll get an I k z, e to the I k z times this, and this. We'll get an e to the minus I k z times this, and this. And we'll get this one, e to the power I k z times this, and this. So there are only, in terms of the exponents, there are only 4 possible combinations. So we'll get, so with these assumptions, we'll get our E field is equal to, all right, here we go. So we'll get first the sum I k z plus ct times something, a bunch of factors, and we'll fill those in. And then we'll have e to the power minus I k z plus ct times a bunch of factors plus ik, and then we'll have a z minus ct times a bunch of factors plus e to the power minus ik z minus ct times a bunch of factors. All right, so this is just going to be a function of these prefactors a's and b's and t's and c's and g's. All right, this looks a little bit looks a little bit baroque, but I hope that you see the following pattern. So this part and this part together again looks like a cosine that has kz plus ct in the argument. So these two together become a cosine. So that looks like a cosine with a k times z plus ct. And this one looks like a sine, if we get the right signs. That was not a pun. Okay, and that is z minus ct. And now we've combined them. So we've sidestepped the trig identities a little bit. We can work out what all of these are, but before we do that, I want to see which ones we want to try to focus on. So this is going to turn out to be a wave that travels in the minus z direction. And this is going to be a wave that travels in the plus z direction. I'm sorry, this is not a cosine, sine. This is also a cosine. So both look like a cosine. So one goes in the plus z direction, that's this one, and the other goes in the minus z direction. So we can decide which one we want, because we can describe waves that are traveling in one direction or traveling in the other direction. So we can decide which one we want. And this is where we say nearpod time. All right, so nearpod. I'm gonna work along with you, just so you see where we're going. So, ladies and gentlemen, I think you all see it now. So the basic idea is here we have a combination of IKZ and IKCT. So we just need to figure out which pairs on this side and on that side are going to give you the right that right exponent. So we need an e to the power ikz. So e to the power ikz, we got that here and we have it here. So these two are going to work together. So we have to factor them and put them in parentheses. So that's why we have an ACZ and an ASZ. So these two. And then we're going to multiply that with whatever is on the time side that has the IKCT. That's an IKCT here and an IKCT there. So that's going to be multiplied with CCT, CST. So those are going to go here. You do the same thing here. Here you have negative and negative. So that means the BCZ and the BSC, making sure there's a minus sign here. And then a negative here. So that's a DCT and a minus DST. ST, there you go. And you do the same thing for the others. Now, the question is, what do we want from this? And that's always something you want to look at. We didn't really drop anything, right? We didn't exclude any kind of situations, except what we did is we said, well, it's easier to work out all the trig identities if we write it in complex notation. But ultimately, the functions that went into this product here, this one, that's a z and a t, this one is real, that one is real. These are both real. In other words, if we have a product of something that's real and then something else that's real, then it should be real. In other words, we need these to be real. What does that mean? Well, that means that if this looks like a cosine, it only looks like a cosine when these two are identical. And this one only looks like a cosine when these two are identical. So we can actually, because we have the freedom to choose these prefactors as we want, we decided to call them this, and we got into this whole tyranny of subscripts. But we didn't actually need it because we can change those prefactors as we want because we haven't really restricted ourselves. So we can change them. And we just insist that this is real. So we insist, because it needs to be, that the red part is real. Okay, what does that mean? Well, we'll get some kind of a prefactor. Let's call it A. Cosine is a different A, so let's call it A prime. Okay. Z plus CT. Okay, and now we insist that the green part is real as well. So we'll call that part B prime, K, Z minus CT. So that's our general solution. So we just get E. ZT is some A cosine K, Z plus CT plus B, and I'm dropping the primes. Might as well not drop them, just to be super consistent. K, Z minus CT. 2, 3, 4. So when you solve these kind of problems, you always need to be a little bit careful. It doesn't hurt to every once in a while to do this, and this is also why I had you do it. But then it's also important to, at some point when you get down in the weeds, to take a step back and say, like, well, what do we really want out of this? So for instance, another approach could have been, so let me show you another approach, and I believe that's the one that I do in the book. It's good to mix it up every once in a while. So we can, for instance, do what I said originally, that we're going to assume that lambda could be positive or negative, and then we just get sum of complex exponents. And then we get those from the very beginning. And then when we do this product, it's going to be less tedious. The nice thing is if you do that, you actually keep the phase degree of freedom, because we actually kind of threw away the phase. So because it could be shifted, but that's not the point. All right, so this is what the electric part of the wave looks like. This is not the most general solution, because like I said, we could shift the phase, but we can always do that by adjusting the origin. And then this one goes in the minus z direction, and this one goes in the plus z direction. And why that is, we will investigate in next class when we look very carefully at these expressions.